So I won't be completing my series on creating a web API because my virtual machine image got corrupted. I tried lots of different ways to restore it, but was unsuccessful. The only change that was made in my computer were Windows operating system updates. So I can only imagine that something changed of how the operating system interacts with the virtual machine. So lesson learned for me is that even if something is not that important and just for fun, it's probably a good idea to make backups. And the second thing is it brings us to the topic I want to talk about today, which is the completion of software projects. If you think back to how software projects used to be, or back in the old days, all software was distributed on physical media. And that forced software developers to actually complete their projects. There is a beginning, middle, and end. But with the advent of digital distribution, it allowed software developers and companies to distribute software that's unfinished and make continuous updates to them as time goes on. Some of the most common examples of that today are probably in the gaming industry, where companies will just distribute a game or release a game that's only half complete and rely on software updates and DLCs to actually provide true content for the game. Now, this would be kind of okay if we were delivering a very strong core software that just gets more and more features over time. But it seems that we are also delivering software with more bugs over time. So a lot of these games sometimes are almost unplayable, right? Compare this with games that were released 20 years ago. The game would be released, and sure, there would be bugs, but the game was usually very playable and very good, has very few bugs. And today we have essentially the opposite. And so I want to talk a little bit about this, the software development process and actual completion of projects. And in order to do this, I want to compare the way that we develop software today to the way that we actually do any other project in our lives, whether it's a construction of a building, making a painting, or even just learning something, like learning how to play an instrument. These things have things that are similar. And so I want to talk about how projects get completed. And the way that projects get completed, the thing that is similar among all these projects is that they start with big changes. So if you think about the construction of some huge building, usually you'll want to level out the earth, right, and create a foundation. And so that means you're going to bring in huge earth movers, and you're moving around literally tons of dirt, right? And then you build the frame of the building, and then you put up the plumbing and the wires and the walls, and then by the end you're doing painting, right? So we see that there are big changes in the beginning of the project, right? There's huge structural things that go on, and by the end there are small changes, right? And this is true of essentially any project, right? When you're learning how to play an instrument, you're very uncoordinated, and by the time that you're a master, you're making very tiny optimizations to how you play the instrument. You're not doing vast changes to how you play an instrument when you're a master. Same thing for a painting. You end up creating very general shapes and colors in the beginning, and then by the end you're filling in very tiny details, right? And so that is how normal projects happen. But if we look at software projects, like say the Linux kernel, and this chart charts or graphs the number of lines of code in the Linux kernel versus time, and we go from 1991 to 2015. You probably can't see the 2015 here because my face is in the way. But that's but that's the timeline for the Linux kernel here, and it has continued on this relatively smooth curve. And so if we think about this, the number of lines of code versus time, we're seeing that the slope of this line is actually getting greater over time, right? So you would expect that in a normal project, there would be a large amount of work, and then there would be just small details near the end. So what this is showing us for software, or for at least for the Linux kernel, is that the amount of work that we're doing on the Linux kernel is actually going up over time. We are not getting anywhere near finished. Even after more than 30 years, we are nowhere near finished with the Linux kernel, right? We're getting more and more work. Now, I don't have access to the source code of the Windows kernel or the Mac OS kernel, but I assume that the project managers have these kinds of charts, and I assume that they look something similar to this. Now, we can also look at several other open source projects that are large, such as Firefox and Chrome, and they have similar charts to this, right? They have nonlinear growth in the amount of source code in there, which tells us that the amount of work that we're putting into these projects is going up over time, right? So we are nowhere near completion for these software projects, right? And in fact, all of these projects look something like this. I chose an exponential curve, but we're seeing that the amount of work that we're putting into these things is going up over time. Now, smaller projects may not see this kind of drastic curve, but a lot of projects, if you look at them, the popular ones, maybe even React and Angular, they have this kind of curve to them, right? They're going up over time, and they're requiring ever more amounts of work. What things should be and how most projects are in the real world is we have a lot of work in the beginning, and we end up going into, after the completion of the project, going into maintenance mode, right? So this is what a healthy project would look like, right? Something like maybe there would be a ramp up near the beginning and down here, so maybe more of kind of a gamma distribution. And I just picked this exponential decay. But this gives us just a rough idea of what a healthy project would look like. We do a lot of work, and then we rapidly ramp down in our work, and we finally get to a maintenance mode where we're just doing a little work to maintain things. But that's not what happens today. Now, we might ask, how does this happen? And the way that this happens is through the software development process. And I think it relates to philosophy of how we approach our development. And I think a good example of this is a little part of an article that Richard Gabriel wrote about Lisp, actually, a long time ago. And there was a little part of that article called The Rise of Worse is Better. And he talked about the philosophy of software development. And he said there were 4 major characteristics in the development of software: simplicity, correctness, consistency, and completeness. And he said the right way of developing software was to value simplicity in both the implementation and the interface. He said the value of correctness is that software should be correct, right? We should make it as correct as possible. He said consistency, that a software should be consistent with itself. It shouldn't have inconsistencies. And that a software should be complete, right? As far as the use cases, there shouldn't really be any crazy edge cases that are not covered. And that, of course, was the right way, or creating this kind of gem of software. And he said the worse way of developing software is to value simplicity, but if you have to make a compromise, compromise in having a simple implementation, right? So whatever is easier to do, just do that, right? Correctness is of course valuable, but if you have to compromise into doing what's easy, right? Same thing with consistency. Consistency is valuable, but if you have to compromise on your consistency, for ease of development and completeness. Of course, you would like things to be complete, but it's much better to just build out the core of what you need and then add in what you things that you find out that you need later. So those are kind of the two philosophies of development of software. And he argues in this article that the worse way of developing software actually has better survival characteristics, right? So if we think of software survival in the world as kind of a Darwinian process, the worse way of development, creating this minimum viable product and then kind of adding on to it over time and just compromising all of these values to just get something done to ship it. It turns out that he said that those have better survival characteristics. So software that is developed in that way is what will be successful in the real world. And so we've had a long time of being able to look at this, of how these things work. And it turns out that he was correct in this original article that the worse way of software development does have better survival characteristics. It may not actually create better software, but it's better at surviving in the real world. And we see this with the way that software development is approached. People always say, build a minimum viable product, and improve it later. We see the philosophy for Facebook for a long time was, build things fast and break things fast, right? And that embodies the worse is better design philosophy, right? We don't see very many successful cases for startups that take a long time to create the perfect gem software, and they release the software into the world and it doesn't really need any updates, right? We don't really see that in the world. The vast majority of software that's shipped today is done with this worse philosophy, so the worse is better philosophy. Now, this is very interesting because Richard Gabriel is comparing software development to a Darwinian process. But the interesting thing is that in a Darwinian, process in the actual world, living beings are not perfect copies, right, of each other, right? There are mistakes that can be made in the genetic, replication process. But in the world of software, every copy of Windows 10 is the same. Every copy of Firefox is the same. And instead of there being many sources of Firefox, there is one source of Firefox, right? There is one source of Windows, right? And even the Linux kernel has a definitive source for the Linux kernel. So even though there's lots of different distributions of putting your own little user interface on top, the major core parts of the Linux kernel are all the same. And so this means that while the world is putting selection pressure on these things, you can't really have any purge of less fit elements in the software. Instead, the pressure is to just ship something that works and just keep piling things on top, right? So instead of having multiple instances of different types of operating systems going around and competing with each other, and having more fit versions, win out, and having these cruft fall away, cruft just stays in there, and we just keep piling things on, right? Because if you think about how a normal person is, a normal person doesn't go around installing Linux on their computer. They go and they buy a computer and they use whatever is on it, and whatever is on it is usually Windows or Mac OS. And so there is no real competition for these things. It just gloms on together, right? You can think of the software development process as kind of a mud ball. And you start out with a pebble-sized version. And in order to put another layer, you need ever larger amounts of mud, right? So the pebble of mud is a certain small amount of mud. But by the time you have a baseball-sized version, you need more mud than you had for the entire pebble, right? And so that's why we see, you know, this kind of thing going on, right? We're keeping on adding on things instead of going back and restructuring things and reorganizing things to be more compact. And so there is no purge of less fit elements, right? And I would argue that we need to add a purge cycle, right? Or an optimization cycle into our software development process, right? So the rough version of this little, you know, Microsoft Paint slide I have here is that in general, we write software, we test the software, and then we deploy the software, right? In fact, especially these days, we have continuous integration, right? And continuous development, right? We're deploying things all the time, right? Back in the old days, we would maybe have one version each year, and now we're pushing out a version every few weeks. And, you know, I could see eventually, you know, software like Firefox or Chrome, maybe they will have daily updates, right? Or maybe multiple times per day. We're just going to continuously go through this cycle where we never take time to reflect on the things that we've written. We just write just enough to get things working, and then we ship it, right? So I would propose that we have something more like this, where we write the software, we test the software, and then we have an optimization cycle. And maybe that optimization cycle makes us reflect on how we wrote things in the first place, and we do some major restructuring and writing the software again, and then we go through test and optimize, and have this kind of cyclic development that has an occasional deployment phase to it, right? So we do a lot more internal and then release versions that can be tested against. And I think this is very important because if you have something like an operating system or a platform like a web browser, it's very useful to have a version of the operating system or web browser that you can say, I am going to test against this. I am going to develop against this. And that way, if there are any bugs that we find in our deployed software, we can have reports and say, hey, I was using this version of the software, you know, and having this kind of slower pace for deployment allows us to have a more stable platform. So I think that's kind of very useful. But what is even more useful is the idea to have optimization, right? To where we can cut out some of the cruft, where we say, okay, I was rushed when I built this thing, right? Because we were trying to ship, but now it's time to go and fix things and make them better. It's time to maybe clean out some of this stuff that's just boilerplate or that was just glued together, and actually think about organizing this a little bit better. And so that's the major idea that I wanted to get across today. I have a lot more that I want to talk about on how to fix this, and even more on what the problem actually is, but I think that's good enough for today. Till next time.